Okay, welcome back. I want to start with a really quick review of what you should know from undergrad about stress strain testing and 1D stress strain description. So if we think of either a tensile or compression test, right, we're going to define an engineering stress, which is the force that's being applied divided by the cross-sectional area of our tensile or compressive specimen. Right? And we can then, if we consider the original area, we have an engineering strain. If we consider the instantaneous area, then we have our true stress. I said strain, didn't I? If we consider our original area, we have an engineering stress. If we consider our instantaneous area, we have our true stress. And notice these are not bold. These are scalar values, right? It's just a force applied divided by the area. And of course, the ratio of the areas is also going to be the ratio of our true stress and engineering stress. Strain is simple. Engineering strain we're going to simply define as our change in length divided by our original length. And to get to a true strain, we need to consider our instantaneous differential change in length divided by the current length, and we're going to integrate that from the original length to where we are now. And if we do that, we get that our true strain is 1 plus the natural log of 1 plus our engineering strain, So just as before, our relationship between stress and strain, our 1D, these 1D scalar, true stress and true strain, is the Young's modulus, right? It's the slope of our stress strain curve is Young's modulus. I want to make a very important point that Young's modulus is 1 over the first term of your compliance tensor, S1111, or as we'll show when we discuss matrix representations of our stiffness and compliance tensor, 1 over S11 if we're using the matrix notation. It is not the first term of the compliance tensor, right? If you do that on an exam, you're going to fail. So make a big note of it right now and circle this, right? I see people make this mistake constantly, both in the class and professionally, right? It's embarrassing the number of material scientists I see at conferences or something, and they'll list C1111 and refer to it as the Young's modulus. That was for tension and compression testing for shear stress and shear strain. Torsional testing, we will define our shear stress as the torque applied times the radius of our sample divided by the polar moment of inertia. And our shear strain is, again, we're still going to say it's the change in length, instantaneous change in length over the length, but this is equal to the tangent of the angle, the angular change here. And from the small angle identity, would just basically say that that's approximately equal to the angle. And the relationship between the shear stress and the shear strain is given by the shear modulus, which is denoted mu and g. Now we know that when we compress something or stretch something, it doesn't just stretch in one direction. But instead, if I start with a block this way, and I apply a tensile load to this sample, it's going to elongate along the 3 direction, but it's also going to contract along the x and the y transverse directions, so the x1 and the x2 directions, right? And the ratio of this extension to contraction defines our Poisson ratio. So the negative of the strain in the 1-1 direction divided by the strain in the 3-3, right? The applied versus the transverse, right, is our Poisson's ratio. And there's a simple relationship between the shear modulus, Young's modulus, and Poisson's ratio. As we'll show, we only need two components, two independent terms to describe isotropic elasticity. And so if we know either the shear modulus and Young's modulus or the shear modulus and Poisson's ratio, we can always figure out the others. So now if our volume were to remain constant, right, our volume naught equals 1, our final volume is given by this, right? And if we know if we multiply this all out, the strain values are very small, so the squares of strain of these strains are exceptionally small. So we basically have this. If we enforce that V equals V naught, there's a screw up a typo. This should be 1 plus epsilon 1, 1. If we do that, we end up with a Poisson's, and substitute this relationship in, we end up with a Poisson's ratio of 1/2. So if our Poisson's ratio is 1/2, it means that our volume is conserved. Most metals have a Poisson's ratio of about 0.3. That's pretty close. Cork and a lot of cellular solids have much lower Poisson's ratio. Cork, the reason why it works for wine bottles so well is because of the Poisson's ratio is so low, is approximately 0, so that when you shove it into the neck of a bottle, it doesn't expand out and break the bottle. Rubber, right, natural rubbers and elastomers have Poisson's ratios that approach 0.5, so they're volume conserving. So natural rubber does not make a very good cork for a wine bottle. It's very difficult. You can't get it in. Okay. So what does the stiffness tensor look like for isotropic materials? So I'm not going to prove it, but you can work it out for yourself, or you can look it up if you're so interested, or you could just take it on faith from me, that if our fourth order tensor is isotropic, we can always write it in a form that looks like this. Right? So we only need 3 parameters to describe our an arbitrary fourth order tensor. Now for elasticity, we plug in stress equals stiffness times strain, and we substitute this in for stress. We get here, and this beta and gamma term get combined. And we can rewrite it in a slightly different form. And so we have stress is lambda I times the trace of K times 2 mu epsilon ij. Right? And so this is our elasticity relationship for isotropic elasticity. And we call these coefficients lambda and mu our that's a better way of saying it. Lemay coefficients, they're called, the Lemay moduli. Lambda does not have a real straightforward physical meaning. Mu is our shear modulus. And of course, this can be inverted to give us strain as a function of stress. Right? This is basically, you'll notice that this is the same form, that equation that I asked you to invert for homework in the first homework assignment, and that we did in class. I just stole the stress equation, isotropic stress equation. Okay. So in terms of, we can always write these elasticity equations in terms of other coefficients, right? So the big one, the one that we always use is Young's modulus and Poisson's ratio, right? So we can write stress is epsilon 1,1. Strain 1,1 is 1 over E sigma 1,1 minus the Poisson's ratio, sigma 2,2 plus sigma 3,3, this quantity. We can, of course, you can, of course, always invert it. But here we have our diagonal terms of strain, and then our shear terms of strain are just related by the shear modulus. The stress divided by the shear modulus. So there's other elastic constants we can define. So if we have a volumetric strain, is the change in volume under a stress, the relationship between the hydrostatic stress and the change in volume, it gives us our bulk modulus, right? And again, because we only need two terms to define the elastic relationship between stress and strain for an isotropic material, we can write the bulk modulus in terms of the Poisson's ratio and Young's modulus. So notice that when Poisson's ratio approaches 1/2, right, when we get a volume conserving, right, we have 2 times 1/2, which is 1, 1 minus 1. This denominator goes to 0, and our bulk modulus goes to infinity, right? And that when our Poisson's ratio is 0, right, that becomes 0, so we have Young's modulus over 3. So the limits of our bulk modulus are Young's modulus divided by 3 for Poisson's ratio 0, and a bulk modulus of infinity as Poisson's ratio approaches 0.5. So we can convert between the coefficients. So this chart just gives you, if I know these two, if I know bulk modulus and Young's modulus, here's how I compute all the other possible elastic coefficients. There's a coefficient on here we haven't talked about yet, M. This is the P wave or the pressure wave modulus, which says if I fully constrain my stress state and strain state to be uniaxial, right? I'm only applying, well, I can't scratch what I said. I can't constrain both stress and strain to be uniaxial. If I constrain strain to be completely uniaxial, meaning I have it's in a, I put my sample in a hole, right, in a really rigid material, and I apply a force, and I only allow it to deform along that axis and not expand out. The relationship, the relationship between the 1,1 component of my stress and the 1,1 component of my strain is my P wave modulus. It has importance in dynamic material testing and earthquakes. Right, it's the type of loading you get under a pressure wave during a earthquake, or the primary wave during an earthquake. Okay. And the last little bit of this part is looking at how these constants vary with respect to materials. So we know that we can surmise that elastic stiffness is going to be closely related to the bond strength, right? The stronger something's bonded, the harder it is to stretch the bond. That's logical. If we consider the stiffness of a bond, right? The curvature of the bond energy, right? That's the derivative of the force with respect to your radius at the radius equals the equilibrium, or the second derivative of our energy with respect to the ratio. Right, we have our force is the stiffness times the change, how much we're displacing it from the original length. So we can say that our elastic stiffness, or Young's modulus, is basically going to be the stiffness divided by the bond length. Right, so it's our Young's modulus is a function of both the curvature of our bond energy and the bond length. Right? So and there's trends, right? As melting temperature increases of our sample, the curvature goes up, meaning our well is deeper, right? And the bond length shortens. So that allows us to write an approximate relationship between the Young's modulus and the melting temperature, and we can come up with then a relationship between the change in Young's modulus, or how the Young's modulus varies with respect to the temperature of the material. And it's pretty, if you play with this relationship, the Young's modulus doesn't change much at low homologous temperatures, right? So going from room temperature to 200 C, you're not going to see a huge change in your Young's modulus. It's not until you approach, a homologous temperature of 0.5, when you get half of melting temperature and above, you start to see changes, and then when you get really close to the melting temperature, your drop-off in Young's modulus becomes pretty significant. The variation in Poisson's ratio across materials, I mentioned that for crystalline solids, the Poisson's ratio is approximately 0.3, right? You can see that works for a pretty good range of metals. There's some odd ones. Beryllium has a Poisson's ratio that's very, very low, very close to 0. Covalent solids also tend to be about 0.3. Ionic, the bonded materials tend to be a little bit lower. So the greater the ionic character, the smaller the Poisson's ratio, as just general trends. Glasses have pretty low Poisson's ratio. Network polymers are all over the place. Obviously, elastomers approach Poisson's ratio of 0.5. Chain polymers tend to be a little higher than metals. Polyethylene is 0.4. Van der Waals solids, so argon at 0, at approaching 0 K, you get Poisson's ratio of about 0.25. There are also other oddballs like foams, certain types of foams that can have negative Poisson's ratio. So that means if I compress them in one direction, they also, the sides on the other directions, they contract in the other directions as well. So they have a significant decrease in volume with compression, and a potentially large increase in volume on tension, during tension. All right, and so we'll stop there, and 2 more short parts, and we'll be done.